Howdy AP Chemistry students, this is section 1.3 on the elemental composition of pure substances. We have a bit to talk about here, so let's get into our learning objective, which is to explain the quantitative relationship between the elemental composition by mass and the empirical formula of a pure substance. Now, this might not make a lot of sense on its own, so let's go through and define some of these the phrases here, especially that of a pure substance. That'll kind of get us to where we're trying to go with this. So in chemistry, a pure substance can refer to multiple things. Either we're talking about individual molecules held together by forces, particularly intermolecular forces, but we'll get into that way later, or a continuous complex arrangement of atoms and ions with a formula unit like CaCl2 representing the ratio of elements. A good distinction between these two types of pure substances. Sugar would be a good example of the first one. Sugar is a molecule like sucrose or glucose. And then when you have solid sugar, you have a bunch of those molecules that are attracted to each other and stuck together. Whereas for a continuous complex arrangement, a good example of that would be table salt, sodium chloride, where you have sodium atoms and chloride atoms that are all stuck together in a big complex arrangement, but there's no individual molecules. So these substances can be either elements, meaning they are composed of just one type of atom, like copper or nitrogen, or they can be a compound that has a ratio of different types of elements. So a good example here is methane. It's a combination of carbon and hydrogen that are in a ratio of 1 to 4. And one quick aside about elemental pure substances. Several of the elements exist as what are called diatomic molecules, di meaning two, atomic meaning atoms. So the molecule consists of two atoms of the same element that are stuck together. These ones in particular are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You'll notice that the chemical formula for all of their pure states is something 2, hydrogen 2, nitrogen 2. That means that pure hydrogen is always going to be a sample of hydrogen molecules that are two hydrogen atoms stuck together, or nitrogen will be two nitrogen atoms stuck together to make a single molecule. This means that you'll never see any of these atoms by themselves. You'll never see just a single hydrogen atom on its own or a single nitrogen atom on its own unless it is an ion. So you can't have neutral hydrogen or neutral nitrogen on their own, but you can have hydrogen ion, which would be H+, and nitrogen ion, which would be N3-, or the example I gave here, oxygen 2-. All of the other elements in the periodic table can exist as pure states by themselves. So you can have basically everything else on its own as a single atom that is not an ion. But a good way to remember which ones are diatomic is to remember the mnemonic device that all diatomics are genuine, meaning that all of the elements that exhibit this property have a name that ends in GEN or INE. You'll notice here hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, iodine, etc. So when we're looking at pure substances that are not molecules, kind of like I gave in the sodium chloride example earlier, we have large continuous structures. For example, this is what silver looks like at the atomic scale. If you had a little particle of silver metal, you'd zoom in further on it and see that you have a bunch of little silver atoms that are all stuck together in an arrangement like this. There's no molecules involved. It's just silicon, or not silicon, silver atoms as far as you can see, if you're to zoom in. Some substances like this are crystalline, meaning that they have a repeating geometric structure called a lattice. A good analogy to explain a crystalline lattice is if, say, you had a bunch of Legos, and say you had those like 1x1 Legos that are just one peg with one little hole on the bottom, and say that was your formula unit, and instead of like building something with different kinds of pieces, you took that one type of Lego and say you got 100 of them, and then you arranged them all in one big structure where it's just that one unit repeating in three dimensions in every direction. That would be a crystal. And a lot of different substances can be crystals. Most people think of crystals and they think of like fancy rocks and stuff like that, but sugar can be crystals. Ice can be crystals. It just means that there is some repeating geometric pattern to it. And some complex structures are non-crystalline. They're just a bunch of random little bits that are stuck together, and there's no repeating geometric pattern. So you can see the difference here in these two diagrams. All right. Also, to further kind of explain these substances that are compounds that have formula units, aka not molecules, is that the formula unit, that sort of chemical formula we gave to it, like the CaCl2 I gave in the example, or NaCl I gave in the example I was talking about earlier, that is our repeating unit. So the formula unit is equal to the like Lego in the example I gave. For sodium chloride, for table salt, your Lego is going to be an Na and a Cl stuck together. And then you're going to stack that Lego in every direction to get the total compound. And the formula unit is always going to give us the ratio in which those different elements occur. So for sodium chloride, we have a 1-to-1 ratio of sodium to chlorine. But if you were to have a calcium chloride compound, that tells us that we have a 1-to-2 ratio of calcium to chloride. And when you look at the zoomed in version of it, you're going to see 2 chlorines for every time a calcium appears in the structure. All right. And a molecule can exist as a pure substance, and it'll either coagulate based on intermolecular forces, kind of like the sugar example. I think these are benzene rings, which is another kind of molecule, but the sugar is going to kind of come together as a crystal like this, where you can see there is sort of a repeating geometric structure to it. I gave ice as an example as well. Or they can be separated into their own individual molecules. So this is pretty distinctive compared to the calcium chloride or sodium chloride example I gave earlier. If you were to break apart sodium chloride, it's going to split up into its individual atoms. Like if you take a cube of salt and put it in water, it's going to dissolve and the sodiums and the chlorides are all going to separate. But if you took a cube of sugar and dropped it into the water, the sugar molecules are still going to be stuck together. They're just going to separate and they're not going to be coagulated into a more meta structure. And the molecules can exist on their own without the complex structure. All right. So whether or not we're looking at a substance that's a molecule or a substance that has a complex structure, there'll always be some sort of formula unit. Though if we're talking about molecules, we're going to call it a molecular formula. So a formula unit is what the terminology we apply to the complex structure in terms of the chemical formula that we give the smallest repeating part, or the molecular formula, which is the actual formula of the molecule. So I gave the example CH₄ earlier. That'll be the molecular formula of methane. You have a molecule that has a carbon with 4 hydrogens surrounding it, and that's going to be your the smallest divisible part of it that we just talked about can exist on its own without the complex structure. But regardless of all of that, it's always going to follow the law of definite proportions, meaning that the formula, the ratio that we see in that formula, whether it's the CH₄, the NaCl, CaCl2, you will always have that ratio of atoms in that substance. Which leads us to another important question. If that ratio is so important, is there a difference between NO2 and N2O4, considering both of these substances have the same ratio of nitrogen to oxygen, being 1:2? And the answer here is actually complicated. The answer is technically yes, but it depends on what we're looking at. In this particular example, NO2, which is called nitrogen dioxide, and N2O4, which is called dinitrogen tetroxide, these are two distinct different molecules. And you can look at their molecular formulas, you can assemble them together and see that these are two different things. They're going to have different chemical properties, different physical properties. However, if we were to do a elemental analysis on these two substances, using what we talked about last time, mass spectroscopy, we're going to run into a little bit of a problem, because if we're going to analyze these, and say we're to do the mass spectrometry where we get the different peaks corresponding to the different atomic masses of the atoms in the sample, we're going to get a peak for nitrogen, and then we're going to get a peak for oxygen. And we're going to see that oxygens are hitting the detector twice as much as nitrogen are. And we're going to see that there's a 1:2 ratio of nitrogen to oxygen. And we're going to get the exact same effect for both of these compounds, even though they're both very different molecules. We're going to see an oxygen peak that is twice as big as the nitrogen peak. So if we had both of these samples in the laboratory, and say we had an unknown sample that was one of them, and we tried to study it using mass spectrometry, we'd have sort of inconclusive results about which one is which because they have the same ratio. Now, if we wanted to figure out which one we were looking at, we'd have to consider a few things, because what we're going to get out of the mass spectrum is something called an empirical formula. An empirical formula is the chemical formula of a molecule or the formula unit of a complex compound. This is always going to show us the lowest common ratio if it's the empirical formula. So if we look at both nitrogen dioxide and dinitrogen tetroxide, they would both have the same empirical formula based off of the mass spectroscopy results. We're going to get a ratio of 1 nitrogen for every 2 oxygens. And if we were to reduce this down to its lowest common ratio, 2 to 4 is the same thing as a 1 to 2 ratio. So the empirical formula, the lowest common ratio formula for both of these compounds, is going to be exactly the same. So say we know from our mass spectrum that our empirical formula of our unknown, which is one of these two substances, is NO2. If we wanted to figure out which one of these two molecules it actually is, we'd also have to consider the molar mass of the compound. So say we did another experiment, it doesn't really matter what it was, but say we were able to calculate that the mass of the compound, the molar mass of the compound was 92.01 grams per mole. This is actually going to give us enough information to identify the unknown, whether it's NO2 or N2O4. And the way we do that is we consider what the molar mass of the empirical formula was. So the molar mass for NO2 is 46.005 grams per mole. Remember, we get that by summing the mass of the atoms involved in the compound multiplied by the number of times they appear. So we'd have 1 nitrogen plus 2 oxygens, and that'll give us this total mass. And we also know that the mass of the actual compound itself is 92.01. So in order to figure out what the actual identity of the compound is, we're going to take the mass of the unknown and divide it by the empirical formula. So we have 92.01 divided by 46.005, and we end up with a value of 2, which means that the actual formula of the substance is going to be 2 times what we found in the empirical formula. And then we'd found out that our actual substance that we're analyzing was N2O4. Even though we got the formula NO2 from the mass spectrum based off of the 1 to 2 ratio, we know that it's actually a 2 to 4 ratio, and we have that compound that I showed earlier in the slides of those 2 nitrogens attached to each other, each with 2 oxygens coming off of them. All right, now let's do a practice of this. So say we know the empirical formula of a compound is CH₂O. We know it has a 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. And we know the molar mass of this compound is 90.08 grams per mole. What is the molecular formula, or else we could call it the actual formula of this compound? We're going to use the same method. We're going to take our empirical formula, which was CH₂O, 30.027 grams per mole, and then we're going to divide the actual molar mass of the compound by the empirical formula. So 90.08 divided by 30.027, and we're going to get 3, which means that the actual formula of this compound is going to be 3 times what it looks like in the empirical formula. So instead of being CH₂O, we're going to have this times 3. So we're going to have 3 C's, 6 H's, and 3 oxygens. So that's how we get this formula at the bottom. So this is going to be called our molecular formula, which based off of the molar mass is the actual formula of this. Remember that the empirical formula just represents what the lowest common ratio is and isn't always definitive of what the actual formula will be. All right, here's a more complicated example of this sort of analysis. So say instead of the ratio where we're given the empirical formula, say the only information we have is the percent mass of each type of atom. So let's say we're analyzing NutraSweet, which is a kind of sugar substitute. And we did some elemental analysis by mass and figured out that it was 57.14% carbon, 6.16% hydrogen, 9.52% nitrogen, and 27.18% oxygen. We know the total molar mass, which is pretty heavy, From this, we can determine both the empirical and molecular formulas of this molecule. So the best way to do this is to sort of make an assumption. Assume that we are to have 100 grams of this NutraSweet molecule. That kind of gives us a convenient way to convert all of our percentages into grams, since we know that those percentages were the percent mass of each atom. So since we had 57.14 gram or percent of carbon, we could say that if we had a 100 gram sample, that would mean we had 57.14 grams of carbon. And then we can divide it by its molar mass, and we end up with 4.76 moles. Then we can do the same thing for hydrogen, nitrogen, and oxygen, and we'll get these 4 values. This tells us that if we were to have a 100 gram sample of NutraSweet, this is how many moles of each of the atoms that we would find in that sample. Now, the way we derive an empirical formula from this is we want to look for the smallest one, which in this case is the nitrogen with 0.680. And we're going to call that the 1 in our formula. We're going to say that we have N1, and then we're going to figure out how many of the other things that we have relative to it, since the N was the smallest one. So we're going to do kind of a similar thing we did before. We're going to take the moles of each atom, and we're then going to divide that by what we call the 1 value. So if we divide 4.76 by 0.680, that tells us we have 7 more times carbon than we do nitrogen. For hydrogen, we have 9 times more hydrogen than we have nitrogen. For the nitrogen, since it's the same value, that's where we get the 1 from. And then for the oxygen, we have 2.5 times the amount, which would imply an empirical formula of C7H9NO 2.5. Remember, N is our 1 in this case. Now, this does not really cut it as an empirical formula, mainly because of this 2.5 here. You can't have a fraction of an atom represented in your compound. So if you end up with something like this where you have non-whole numbers for your empirical formula, you need to find some number that you can multiply the whole thing by in order to get whole numbers. Since this is 0.5, that's easy enough. If we just multiply everything by 2, the 2.5 will become 5. So we end up with the actual formula C14H18N2O5. And this totally works as an empirical formula because this is the lowest common ratio, like 2, 5. We can't divide this by anything else to make it more reduced. Now, we were given the molar mass of the whole compound, so now we need to figure out if our empirical formula is also the molecular formula. So if we were to take this really complicated compound and calculate the molar mass like we're used to, multiplying each of our atomic masses by the number of times it appears in the compound, we'd end up with the same value that we have for the molar mass, which tells us that in this specific circumstance, the empirical formula and the molecular formula are the same, which is totally fine. We saw that earlier with, like, say we were to have NO2, nitrogen dioxide. The molecular formula and the empirical formula are going to be the same because the molecular formula is basically the smallest ratio that you can get in that, and have the ratio be the same, if that makes sense. So that is all I have on this topic, and I'll see you in the next one.